So welcome everyone. Thank you for joining this talk today. It's really good to see you joining in so many numbers, and I think it's really, at least for me, pleasant to see that this event is scaling in person now as well. And I think this is the topic of our conversation today. So let's get it going. So firstly, before we dive into, has anybody heard of offline beam packing before? Okay, a couple of hands. For other ones, we will dive into details later on, but in the nutshell, it's just a fancy name for defragmentation or optimization. So don't worry about it at this point. Right. So can I get a raise of hands from people that are using Kubernetes clusters and not using any kind of auto scaling or have dealt with clusters like that? Okay, couple of hands. Okay, so it seems like I don't have to convince you about auto-scaling then. It would be interesting to kind of discuss reasons why you're not using that later on after this talk. But I guess we could sum it up probably because auto-scaling is hard, specifically if you want to get it right. It's probably quite a hard problem to kind of address and probably kind of put it in place properly. So when we're doing auto-scaling in Kubernetes, I'm assuming that everybody can relate to it. Sometimes can feel like, pushing a boulder up the hill. Sometimes it can be like this constant battle between what do we want out of the Kubernetes cluster? Is it right scaled? Is it too expensive? I think most of the scaling solutions that are out there are trying to tackle this specific problem. So we're trying to not over-provision the cluster and at the same time save some money, or not kind of use too much money on the compute that we kind of provision to our Kubernetes clusters. Got a short introduction from Nick already, but I'm head of consultancy at the Scale Factory. We are a B2B SaaS AWS consultancy, so purely working on AWS workloads. That's one of the reasons why I'll be talking about Karpenter, which is an AWS project. But it was developed and designed with kind of the openness in mind, so it can be applied to any kind of provider that you run your Kubernetes clusters in. Like I said, I've been in the industry for a while, worked with different technologies, wearing different hats, but I think throughout my career, most of my roles were somehow related to open source, which I really feel passionate about. I'm also an open source contributor. You can probably find me in a couple of repos, specifically Helm chart for Argo CD. I'm also a HashiCorp ambassador, OpenUK ambassador since recently. And when I'm not working, I'm really a fan of traveling and kind of exploring new places as well, which we are open to do so now again. So that's cool. Right. So what we're going to cover today, very quickly. So we're going to quickly have a look at Kubernetes and node auto-scaling specifically. So we won't be talking about the pod scaling, but specifically we're going to focus on the node auto-scaling. We're going to have a look at the Karpenter. What kind of solution is it? What does it provide for us if we are doing node auto-scaling? So we're going to start with architecture, just speak a little bit from the high level, what the advantages of it are. How does it manage the node lifecycle management? And specifically what I want to focus on today is, because I had a similar talk last year when we were still online, I want to focus on a new feature that just landed in Karpenter, which is actually the node consolidation. And we're going to have a look why is it important and why I believe this is really a killer feature for that product. And then seems like I'm the only brave one today. I'm going to show a live demo, so fingers crossed for that. I've been to a couple of talks. Nobody dared to use the live demo, so I hope that goes well. And we're going to wrap it up at the end. Probably not quite with beers yet, but we will have beers after we're done. Cool. All right, so quickly, when you're doing Kubernetes node scaling, you're probably familiar with the concept that out of the box, you won't get any scaling of your node. So you either manually provision your compute or you don't have any compute, right? It's simple as that. And for the types of scaling that we can do in Kubernetes is we can do horizontal or vertical scaling. So for horizontal, we just throw more instances in And this is usually referred to as scaling out. And the vertical scaling would be increasing the instance sizes and thus having more resources available to us. Probably the most common auto-scaling solution, kind of de facto de facto standard that we have in the industry, and probably most widely adopted one, is cluster autoscaler. It's an open source solution, vendor neutral, and automatically adjusts our cluster size and kind of tries to optimize it for efficiency. It's also battle tested as well, so you can spin up to a few thousand nodes with 30 or so nodes per, pods per node. It really depends on how quickly you run out of the CNI interfaces or any other limitations that you might face on the node, such as resources. And its main feature is it's using the cloud building blocks. So it has a concept of node groups. It's not really an object in Kubernetes, but it's a high-level construct where you group nodes together in a group, and those would have similar properties such as instance labels, instance types. We would usually do the AZ spread using the same node groups, and that poses specific challenges, specifically when you want to have things like cross AZ spread or kind of different complex scenarios we want to optimize for specific workloads. And I think the issue which Karpenter is trying to solve that maybe cluster autoscaling is falling short at is specifically if you have you can only scale up the same types of instances, right? I think this is kind of the biggest shortfall where I think cluster autoscaler is probably not handling that well, or it just comes with different kind of from different history and different kind of consumptions. But Karpenter is trying to solve exactly that, and we're going to see that just in a bit. So if we quickly have a kind of a 10,000 foot kind of a high level architectural overview of Karpenter, what it is, it's node lifecycle management solution. So how it works on really high level is you would usually spin up pods through deployments or replica sets or whatever you use to kind of spin up your pods. And the scheduler would usually go and schedule those pods on the existing capacity you might have on your cluster. But the trick is, what happens when you're trying to schedule pods and you don't have capacity available? In that case, obviously, you need to use an auto-scaling solution. And in this case, Karpenter would kind of notice there are unscheduled pods, and it would use the capacity that unscheduled pods need to kind of run, calculate that based on the instance types that are available or that you specify, spin them up, make it part of the cluster, and enable scheduler to kind of schedule those pods on those new nodes that have been just provisioned. So if we have a quick look how that actually happens, so kind of a nice illustration, we have Kubernetes cluster with a control plane, users trying to access the workloads, and we have, if we look at the really simplified example here, we have a node with a pod running on it, and obviously we want to spin up a new pod. We can fit that in the existing capacity. But like I said, what happens is when we try to kind of schedule another pod and we don't have the capacity, that pod actually ends up in unscheduled state. And if we want to schedule that on our Kubernetes cluster, what we need to do is just spin up a new node. If using a cluster autoscaler, it would be the same capacity and just schedule the pod there. And this could kind of go on and on, unless we want to schedule a pod that's larger than the capacity that we have currently available. And that pod actually ends up in unscheduled state, and it doesn't fit in the same kind of box that we already kind of have. So that kind of poses the problem with the cluster autoscaler, right? And like I said, Karpenter is trying to solve exactly like that. And what it actually knows how to do is it removes the concept of node groups and just adds capacity directly to your cluster. So it spin up the right size node of the capacity you need, where your pod can actually fit into now. And your nodes would actually look completely different based on the workloads which you want to schedule on it. So I already started kind of covering some basic key concepts. So if we go through that really quickly, like I said, it runs in this kind of a basic loop where it would watch, evaluate, provision, and remove the resources based on the workloads you're trying to schedule. It has a really straightforward setup. So you could kind of trim it down to basically 4 steps, which would be you have to provision IAM roles if you're deploying it to AWS. In other providers, that might be different, but some roles that it has permission to kind of interact with the cloud environment. You need to install the controllers, apply the provisional CRD configuration, and deploy workloads. And that's literally what you need to do. It's a very straightforward kind of installation. And when it kind of when you're scheduling your workloads, it actually obeys all the constraints when scheduling. So when I say all the constraints, it means that it would obey your pod disruption budget, topology spread constraints, node selectors, node affinity, anti-affinity, and everything else. It's also aware of some well-known labels as provisioning constraints as well. So you can specify what kind of nodes you want to spin up. Either they are AMD 64 or instance types. It actually has the selector for instance classes as well. So it doesn't have to be specific instance that you need to specify there. You can define in which availability zone or in which availability zone you want to run it, in which region. And obviously, you can define it on demand on spot instances. So if we further look how it manages the capacity is when the capacity is launched, it's using APIs directly. So like I said, it's direct provisioning of the capacity. When the capacity is initially provisioned, it's using online big packing. And maybe this is a good point for me to kind of explain what bin packing is in the first place. So for those who are not aware of it, the bin packing is actually an optimization problem where you try to fit the items of different sizes into a finite number of bins or containers, and those have a given capacity. So it's a kind of a well-known NP complete optimization problem. And in order to kind of optimize it a bit, what Karpenter is doing is it's actually using first fit descending algorithm. So what that means is you would start with the biggest item, sort it down to the smallest one, and just fit it into the first container that it can actually fit it to. So quite straightforward and really not much more to it than that. So that's an online bin packing. If I quickly mention what the difference is between online and offline, like I said before, in online, items are kind of coming in sequentially, whereas if offline, it's kind of rearranging the initial capacity that you currently run on and try to find the optimized containers that you need to fit your current workload into. So this is the provisioning capacity, right? So opposed to that, we have deprovisioning capacity as well. So when we deprovision the nodes, or when Karpenter deprovision the nodes, when that actually happens is first, if we delete the provisioner, that when I say delete provisioner, I mean the CRD for it. So in that case, it would remove all the nodes that will be left without so-called a parent. But they have a concept of so-called reparenting nodes. So what you can actually do before you delete the provisioner, you can actually relabel the nodes with the new provisioner labels, and that would prevent it being deleted. Then the second bit is the finalizer. So for example, if you go and delete a node, just say kubectl node delete node, it would actually cordon the node, drain it, and terminate it in a clean way because there is a finalizer attached to it. So it doesn't interfere with any other tooling that you might have for lifecycle management outside of it. Obviously, the nodes will be deprovisioned when they become empty. There are a couple of parameters you can set. The TTL seconds after empty. That means that it would wait for a specific amount of time before it deletes the node, just to kind of prevent deleting nodes too quickly. Or you can set the node expiry, which is called TTL seconds until expired, which actually is quite useful if you work in a compliance space or you have a compliance requirement where your nodes need to be recycled after a specific time. So for example, you say all our nodes need to be recycled every month. You just set the timeout and it would automatically go and reprovision your nodes every month. Then it also obeys the interruptions. So it watches for the upcoming kind of interruption events that would affect the nodes, such as terminating the node, stopping the node, maintenance events from, in this example, like AWS or any other cloud provider. or kind of spot events as well. So for example, spot prices might change or anything else that affects the cost of your resources. And of course, the consolidation, which we're gonna kind of focus on slightly in a bit. So the consolidation bit is actively trying to reduce the cluster costs by kind of monitoring all those events and trying to figure out the optimal node configuration for your current workload. So it will always try to adapt to whatever you're currently running in your cluster. Right, so the capacity consolidation, like I mentioned, a.k.a. offline bin packing. I'm not trying to be fancy here, but this is how actually they call it. So it's constantly trying to rebalance all the node workloads based on the utilization of those nodes. So it would constantly monitor the utilization. And when I say utilization, what it actually checks is for requests utilization and not the actual utilization of the nodes. And that's why you have to be kind of careful and kind of try to properly mark your workloads with the requests and limits that actually they needed. So what are the mechanisms for the cluster consolidation? It uses two mechanisms. So it would be either delete or replace. So when I say delete, it means that in case like I said, the node is empty or the workload capacity can fit or be spread around other nodes, it would kind of remove those workloads onto the other nodes and just remove the node in case it becomes empty. And this mechanism works for both the on-demand and spot instances, whereas the replace only works on on-demand. And the reason why that mechanism is not intentionally turned on for the spot instances is because the spot instances are using price capacity optimized strategy. And what that actually means is that it wouldn't be optimal to kind of constantly try to replace the spot instances. It would just kind of start to kind of introduce too much interruption to the workload. So they intentionally kind of opted out of that strategy. And it would sometimes even not lead to the cheapest possible outcome as well. Like I said, it always tries to optimize for the cost. So when I say optimizes for the cost, I mean without kind of interfering a lot of interruptions. So what it actually does is when Karpenter figures out that it can actually replace the node with an existing node, it would firstly spin up a new one, wait until it's ready, move the workloads across, and after that's done, it would remove the empty node. So it would try to avoid interrupting your workloads availability as much as possible. It does obey the scheduling constraints, like I said, the pod disruption budgets, the finity topology, and others. Also the grace period and expiration TTL as well, if you have that set. And in case of instance unhealthy events, it would kind of obey that as well. Interesting thing, when there are multiple nodes available that could be either deleted or replaced, it always kind of optimizes for the least disruption. And that means like it would always pick nodes with least spots running. It would always pick nodes that would expire the soonest, that would kind of be doomed to be replaced anyway, or the nodes with the lower priority pods. So it always kind of tries to be intelligent about the decisions that it's making. So it's not just going widely across your fleet of nodes and playing the chaos monkey on top of it, like saying, oh, I'm just going to delete everything. It's fine, right? Everything is kind of disposable nowadays in cloud native. Right. Let's have a quick look how the provision or CRD looks like. It's not a complete example, but it's a fairly complete example, or at least if you start with that, I think you would be quite well off. So the reason why I haven't put everything on it, it's first of all, I want to make it readable, and second of all, probably easy to grasp on if you haven't seen it before. So what I want to show you here is as part of the spec, we have a section called requirements. And as I mentioned before, it kind of recognizes all the well-known labels. So for example, we can say, we only want to schedule in on specific types of instances. So specifically, we want to avoid like expensive ones or like really small ones, or maybe we want to avoid like burstable instances, which might have trouble kind of providing the capacity we want for. Then we can specify the zone where we want those instances to run. So for example, it's probably a weird example, but we kind of discriminating against the zone B here. We're saying only want to spin in A and C, just for the sake of it. And it will always obey that, so you would never see an instance running there. What I want to mention as part of that as well is what's also aware of. So for example, if you have a volume attached to your workloads, the volume is usually a kind of created in an AZ. So it also knows how to check for that. So it would always schedule your workload in a zone that kind of meets all the requirements for the workload. So it wouldn't try to schedule it in a zone that the workload couldn't even run. And then obviously we can specify like things like architecture or a capacity type as well. Then a little bit lower, we have limits. What limits means is we can set a limit on a provisioner. And what that actually means is you can prevent the provisioner to provision more capacity, overall kind of summarized more capacity that you want. And this is specifically because this actually infers kind of hard costs down the line. You have to pay for it. That's why you have this kind of a safeguard on resources where you can say, I want to provision maximum 1000 CPU capacity using that provision and not more, even if the workload would require it, right? And you can kind of specify like memory limits as well. But I think for the sake of the example, I think it's easier to kind of think in one dimension. That's why I'm just going to use the CPU throughout my kind of demo as well. And then the last bit is the provider section. This is not the latest version of Provisioner. You can still use it, but it's becoming deprecated because they have actually replaced that bit with its own CRD. So there is a CRD called AWS Node Template, I think it's called. We're going to see in an example a little bit more. And what it actually does is you can actually specify all the bits that you would usually specify in the node template. So it kind of removes the need of actually having to go create a node template somewhere in your provider and define what kind of node is going to be spun up. So everything can be controlled through the CRD now. So in this example, I'm just kind of using the mandatory ones, so the subnet selector, so it knows where to kind of put the nodes in, which subnets, and the security group selectors, so it knows which security groups it will use spinning up those resources. And I'm just using the default instance profile, which would be a set of permissions that we're going to see in a bit. And the interesting bit here is a flag called consolidation enabled. We turn that on because obviously we want to demonstrate that how it actually uses that to kind of optimize our workloads. Right. Are we ready for demo? Or you want more slides? Yeah. Okay, perfect. Yeah, I was just getting worried. I mean, I do have backup slides though. So, all right, so let's jump into it. Okay, that's going to be interesting because I have to use this screen for you as well. So what we're going to quickly do here is...
Folks, maybe sense to the back. Is it clear?
Okay, perfect. So what I'm going to do here is going to run a couple of things, so not this one. So what I'm going to do is, oh yeah, let me first, what I'm going to do, I'm going to deploy the controllers first because this is going to take about a minute or so. So just to get a feel what's happening is, so it's a Helm chart. I'm going to show you what that looks like, just to kind of give you a glimpse what we have. So what I have here is an EKS, vanilla EKS cluster. It doesn't have anything deploying it. It's empty. And what I did now is I just deployed a Helm chart for Karpenter. And what it's doing, it's out of the box, it's being provisioned in HA mode. So it would immediately start with two controllers. In case one of them fails, they have like a leader selection mechanism built in as well. So if you kill one, it would still kind of do the provisioning. And what I'm doing as part of that is, as we wait this kind of spin up, I'm just going to show you the nodes quickly. What do we have here? As you can see, I'm actually using Fargate for this example. And the reason for that is I think it's a really good use case for it, specifically because we obviously don't want to manage nodes that manage autoscaler. I think that's a really good way of kind of using Fargate in this example. So what we're going to do is we're using a selector on the namespace saying everything that's in the namespace Karpenter. It's just going to be scheduled in Fargate, and we don't want to kind of worry about it. It's just going to be run by Amazon in this case. So as you see, it spun up 2 new Fargate nodes to kind of run those pods on, and they're actually running, which is faster than I anticipated, but that's fine. So let's quickly have a look what I've already deployed, like I mentioned. Can somebody shut down the lights in the background? It's probably going to be easy to see. If not, I really hope that's clear. If it's not, I can probably make it white, and that's going to be easier to read. Oh, perfect. Can people see that in the back? No? That's worse, Nick. Better? Okay, perfect. So I just want to show you what I've already deployed. So I already deployed, what did I deploy? CloudFormation Stack, which is just a basic permissions for Karpenter to kind of deploy resources for us. We created IAM role, bind it to the service account that we're going to use for Karpenter, and that's literally from the permission set that we have to do. The second bit, like I said, the controllers, it's literally just deploying a Helm chart. It's really not much into it. The only thing that maybe it's worth noticing is we're specifying the service account. So as I said before, we did create the permissions for it. We're just mapping to it now. And we're just passing a couple of settings down to it, like what's the cluster name, what is its endpoint, and the instance profile is going to use when it spins up its capacity. And what we're going to do next is we're going to deploy a provisioner. That's really bad. Okay. What we're going to quickly do here is, that's slightly better, not much, but still. The provisioner looks exactly what I show you. It's using slightly more up-to-date CRDs. So what it actually means is I'm actually selecting from the instance category instead of specific instances. So I'm saying I'm only allowing classes C, M, and TG, T4G, so the Graviton instances. I'm kind of limiting it to maximum 65 CPUs, so I don't want instances larger than that. And there are a couple of other things that you can do that I'm kind of intentionally not doing right now, which is I can specify like the hypervisor type, like Nitro, or you can actually specify which specific values you want for the CPU, and so on. I'm specifying limits like I posted there, and what I'm using here is the provider reference, like I said, because they want to make it provider independent and they're still waiting for the first contribution for other provider. You can actually use that as a CRD, which is an AWS node template in this case, which is a default one. And you can actually specify the same things that I showed you there before, like you can attach specific tags to it, you can have security group selectors and things like that. So let's go out of this, and what we're going to do as the last bit, I'm going to create a really simple deployment. You obviously cannot see that as well, so that's why I'm opening this up. So deployment is really, really simple. Like what I'm doing here, I'm actually deploying a deployment which spins up actually a pause container, right? So it's not going to do anything. The reason why I'm doing that is I want to simulate the requests. That's why I actually put in a resource request of CPU1. Because this is going to kind of eat up my CPU utilization, and we will be able to see what actually that does. So let's see what we have open here. So we have our nodes, we have our pods. Let's open the logs. So we actually want to see what's happening. And what I want to do as a first thing is we're going to scale up the deployment. Let's go for one first. Let's see what happens. So as you can see here, the Karpenter actually detected they were actually unscheduled pods, and it actually figure out the instance type, which in this case is C6A large, and that should kind of satisfy our request for the specific pod that we want to spin up. And it kind of calculated that. It kind of simulated that that would kind of satisfy the need of one CPU request. And because I really want to make that slightly quicker, let's go to 10. What I actually want to show you is, you're going to see when I kind of scale it up a bit, it would immediately add the pods. You're going to notice this one is already in container creating, and other ones are in pending, right? So obviously that one already no, it's still in pending now. What I wanted to show is they're still in pending. And if we check the nodes here, the nodes, oh yeah, because it actually figured out it's going to be a different one. So spinning up this one now, you're going to see it entered the not ready state. But if we check here, they're already in container creating, even though the node is not ready. The reason why that's happening is because Karpenter is working together with the scheduler in the way that when the node is spun up, it has the information which node that's going to be. So it's kind of preempting that and binding the pods to the node that's going to actually appear at some point. And that's what it's actually doing. So when the node is available, so when the node is ready, which is just about now, you're going to see the container is going to immediately start running as soon as the image is pulled down, right? So that's fairly quick. So what I wanted to actually show you as well is let's scale it up a bit. Let's keep it a notch. So what I'm actually doing, I'm gonna scale it up to 100, and I'm actually interested in this view now. So what we actually see here is, because I scaled it up, it calculated, oh, I need 2 additional nodes to kind of satisfy my additional 90 pods that I want to schedule. So it's kind of spinning those up. That should come up in a minute or so. The spin up is usually slightly less than a minute, just shy of a minute. So we are like 25 seconds now. So they should appear any moment now. But what I wanted to show you is actually just gonna enter a couple of empty spaces here so we'll see what's doing. So this kind of did the same thing that it did before, kind of figure out, okay, we have 90 pods we want to schedule. What the split was, I think it's going to be doing something like 85 and something else. So obviously that was just provision. And what it actually kind of discovered is, as you can see, it says deprovisioning via the consolidation replace. And what that actually means is consolidation replace is actually, if I move here, you're going to see when everything kind of spun up, it was distributed. It kind of figured out, we have really low utilization. If you check the utilization there, we have 97, 95, and 84. And that's just based on the requests, right? And it says like, okay, we probably can do better than that. Like specifically, I think it's going to be replacing the one that's 84, I think. Sorry. Yes, 84 with something smaller. So it's going to fit on a smaller instance and just remove that one as it's provisioned. And I think this is where the real power of optimization comes in, where it will constantly reevaluate your workloads and try to find the best fit node for the workloads without me doing anything on it, right? Like I didn't touch anything. I just provisioned my workloads. I said, here we go. I want more pods. And Karpenter controller just went, oh, fine. We can actually schedule it elsewhere. And fine. And it kind of does the same thing for deletion, which I don't believe we have time for. Nick was kindly reminding me that we're getting towards the end. Let me try to get to my slides. I only have one left. So just gonna quickly find one because I didn't press the right button. Here we go. Quickly, conclusions. Capacity provision planning is hard. I think everybody in this room can agree to that. The key advantages of using Karpenter, obviously I'm biased, we mostly work with AWS, but like I said, it's kind of designed with openness in mind, so it's an open source project as well. It's flexible, it really lowers complexity of kind of managing the node scalability, and it's portable as well. Like I said, they have opened it up from the start. It was incubated project. I think there are conversations if maybe donating that to the CNCF, don't hold me to it. But I believe this is something that's in the cards. It's really performant, so the performance provisioning latency is currently around a minute. As you saw before, they're trying to get it down to 15 seconds, which I think is quite awesome. And like I said, consolidation does the deletion. Either the node is empty or the workloads can be moved, or it can replace the node based on the best fit. And yeah, it handles all the interruptions as well. Please keep in mind, currently only supported provider is AWS. Interruption handling is managed, but the spot rebalance recommendations is still something they're working on. And it's definitely not appropriate for the workloads that are could not be interrupted. Thank you for listening. And if there are any questions, I'm happy to take them outside because I believe I'm slightly over time. Thank you very much.